Okay, we can. So yeah, we can just get started. Hey everyone, my name is Ajit. Today we're going to be discussing about the Cameo paper. The authors, the name of the authors have been listed here. It seems like it's a joint collaboration between University of Illinois, Urbana-Champaign, University of Edinburgh, Wisconsin-Madison, and Microsoft. So let's get started with it. Oops. Yeah, so like the modern stream processing systems that are typically run by these large companies, they ingest a lot of data, and to scale such systems, typically those companies run these data pipelines made up of multiple operators across multiple machines. Like you have a network of machines on which these typically will be run, so that you can scale. And at the same time, you also need to. They also are concerned about the total cost of ownership. They want to keep it low. So what they do is that it'll be deployed in a multi-tenant fashion, where multiple data pipelines would be deployed in the same underlying infrastructure. So you'd have multiple operators co-located on the same machines. Now, like the goals that the overarching goals that companies that operate such systems strive to achieve are like the two goals essentially. One is like have high resource utilization, and also provide some kind of performance isolation to the applications themselves. So the paper claims that the existing state-of-the-art systems that are out there, like, I mean, in general, like, the resource provisioning aspect of it itself is kind of challenging, because you have variability in the workload, and in the sense that some of the workloads could be bursty in nature, some of them are smooth, but yeah. So that when you in a multi-tenant fashion system, you would see a lot of variability, and then the applications that are dependent on such systems also have latency requirements, and it would differ across the applications as well. So now the latency requirements they have some associated, like, SLAs with it. There can be SLAs, and if you don't meet the latency requirements, then the SLAs will be breached, and it will have its own set of repercussions. So the claim, the paper claims that the existing systems that are there, kind of achieving both these goals is kind of hard. So typical deployments would look something like the following, where deployments where you can't afford to miss out on the latency requirements. You typically over provision, like, this kind of shows that you have dedicated resources assigned to a specific data pipeline. So this here you might be able to hit the latency requirements, but then from a resource utilization point of view, you would have over provisioned. And the other extreme is that in order to keep the resource utilization high, you would like multiplex all the data pipelines across the infrastructure that is there, but then you would not be able to meet the latency requirements. Like, so these are the. So you kind of get one out of the two with the existing systems, and that's what Cameo tries to like solve. So it tries to achieve both high resource utilization and offer guaranteed performance characteristics. So Cameo itself is it's kind of based on an event-driven architecture, where the operators of a particular particular data pipeline are run as serverless functions. I think underneath it uses the Azure Orleans actor framework to achieve this, and they have enhanced that by by having this fine-grained scheduling capabilities. So by fine-grained, what I mean is that Cameo tries to identify and the priority of every single message that is coming into the system, and thereby it can actually schedule the more important work ahead of not so important ones. and in Cameo itself, the architecture level, it comprises of two main components. One is the scheduling strategy. Scheduling strategy enables us to determine the priorities of every single message flowing through the system, and then there is scheduling framework, which, like, once the priority of a message has been determined, like how do you schedule those messages on the operators. So the scheduling actually takes place at a message level, and as well as at an operator level. Like, you have multiple operators co-located on the same underlying infrastructure. So you want to decide which one to run. So you kind of prioritize between the operators as well. So that's what Cameo tries to solve. Yeah, maybe we can talk a little bit more about the scheduling strategy. So scheduling strategy kind of involves defining the policies that enables us to have this fine-grained scheduling, which kind of like one of the important things that they look at is like, I think it probably depends upon what type of scheduling algorithm that we're trying to use. So I think in the paper there's a reference to the least laxity based scheduling, and there are a bunch of others, but in least laxity, I think they look at the least, the more they kind of pick up the message which has the least laxity, least flexibility, and try to prioritize them over the others. That kind of boils down to like figuring out what the deadline is, and to determine all of these, like determine the priority of a message based on this information. You kind of need the deadline of a message that needs to be processed, like the time before which it needs to be processed, and also the cost of the message processing at every single stage in the data pipeline. So it needs the information like that. And in order to be able to get this information, Cameo also makes use of topology awareness and query semantics awareness. It tries to get this information to improve the prioritization capability. Maybe we could probably walk through some of the examples to see what topology awareness and query semantics mean. So let's say, I mean, the diagrams I have taken it out from the slides or the paper. So here we have two different types of queries that are being run, and so this is two separate data pipelines, and each of them actually are made up of one operators. Operator O1 he runs like a bulk analytics query, which has a larger target latencies. Like every request that has come in should be processed, like when they are ready, they should be processed within 100 milliseconds is the target latency that is there. But then it is actually performing a windowed operation, like it picks up all the messages, let's say, that arrive within 1,000 millisecond window, and then performs a summation on that. And the second query is like latency sensitive. It is like it's probably looking for some errors, and then you want to act on them very quickly as soon as you can. So here it has the latency constraints are quite stricter. The target latency is 50 milliseconds in this case. And let's say if you assume the arrival of messages like this, like M1, M2, M3, and M4, M1 and M2 should be processed by O1, and M2 and M4 to be processed by O2, based on the target latencies, right? And the type of queries that are being run. So M2 and M4 they have the shortest deadlines, and if they ever get processed beyond these lines, and we are creating a violation. As far as M1 and M3 are concerned, the violation point is somewhere here. Like this also accounts for the 1,000 millisecond window size that we have. So in order to get the best out of this, right, the schedule should look something like this, where the shortest deadline ones are actually processed first, and that way none of them are violated. But then if you use the like whatever is out there, right, the vanilla, let's say Orleans, or if you implement some without any topology awareness, if you implement some scheduling algorithms, so typically you would see a lot of violations. Like if one of the example is like a FIFO based thing, like based on the message arrival, if you start scheduling them, then clearly M1 would be picked up first, but M2 and M4 would suffer because they're beyond their latency constraints. So now with topology awareness, you can do somewhat better. Like what topology awareness here means is that like I mean, like you probably take into account what the latency of every single message is, and based on the latency, you figure out the deadline, right? Like this is the thing that needs to be executed before. So and you kind of line them up or sort them up based on the deadline, and with that, we can see that like the violation on M2 is resolved, but M4 still suffers from the violation because just by looking at the latency information, we would deduce that M1 should be like executed before like this particular mark, and we would prioritize M1 before M4, and thus M4 will suffer from a violation. So the claim is that topology awareness in itself is not sufficient to get better better at resolving all the violations. So we also need the claim is that we also need to be query semantics aware. So the next with query semantics, what they're saying is that we kind of know that M1 and M3 are being processed by a query which is windowed operation, and that means that these messages won't be processed until the window time is expired. So there's no need for them to be processed or picked up by the scheduler immediately, so they can be delayed. That's kind of denoted by this the blue lines here, the blue space here. So with this information, the scheduler can actually prioritize M2 and M4 before M1 and M3 are processed, and that way you kind of get the best schedule out of it and see lesser violations. So yeah, that's the claim. So Cameo tries to be both topology aware and semantics aware, query semantics aware, to generate the priorities of the messages. And so now, so one of the crucial things here is that we need to figure out what the message deadline is in order to be able to prioritize them, and to figure out what, and like the message deadline is denoted by DDLM, which this is the deadline of a specific message M, and to compute this, there are multiple variables at play. So one is that every single message that is presented to the pipeline will also be will have a latency constraint associated with it, which is denoted L. This is the time when the before which the message should be processed by the pipeline. And there's a notion of frontier time from frontier time, which kind of denotes the time at which the message is ready to be processed. So that is frontier time, and then we also need to take into account the cost of execution of a message at a given by a given operator, and if it is like a multi-stage a multi-stage pipeline that we have, which is typically the case, we also need to figure out what would be the cost of executing that message by the downstream operators. So once we have all of these variables, like calculating the deadline is kind of straightforward. I think the challenge is in figuring out these the downstream part of it, like how do we figure out what's the cost, and in order to be able to do that, we like clearly we should be like sending back some information in both ways, right? Like you might want to send down some priority information to the downstream operator so that it can calculate its priority better. Similarly, to make your priority calculation more robust, you need the information about, let's say, the cost of execution by a downstream information. If that information is available at an upstream operator, then the priority calculation can be much better. So we kind of need this information to be like flowing both downstream and upstream, and that is one of the next components that make up Cameo. So that's where the scheduling framework comes into play. So there are like three overarching challenges that the paper talks about. Like one is like how do we propagate this static and dynamic priority information between the operators, and another thing is that these priority is actually being calculated at a per message level, right? So how do we perform these priority assignment efficiently and scale well with the volume of messages flowing through the system? So that's another thing. Like if you have that's one of the challenges that they want to solve. And the other thing is that for every single data pipeline, the way you want to calculate a priority could differ. So now, like, how would you give this ability wherein the way you calculate priority can be customized, but the underlying scheduling scheduler itself will be the same, and just so it's just the policies needs to be changed. So those are the overarching challenges that they identified, and the scheduling framework that they have implemented tries to solve them. So as far as the first challenge is concerned, like how do you propagate information about, so they introduced the notion of scheduling contexts. So this contains all the information about a priority, and this will be sent along with the message, like both downstream and upstream. So there are two different types of context depending upon the flow. So if you're going downstream, then typically there's something called as a priority context will be generated and sent down to the downstream operators. This would include the local priority and the global priority. So local priority at a given operator, the local priority is actually used for scheduling the messages within the operator, and the global priority actually is used to schedule the operators themselves. Like, because operators are co-located, some of the operators might have higher priority than the others. So this allows us, the system allows to schedule between them as well. And then once so now to send the information back up the data pipeline, something called as reply context will be used, and this would actually have information, something like what was the cost of executing processing cost of execution of a message at a given downstream. That information is encoded into this and sent back up, and whoever receives this particular reply context would use the information there and aggregate them all, and that way the priority calculation can be improved at that particular level. Then like, this is running on Orleans, right? Like, and the operators so now we need a way for the operators to actually embed this information in the messages that they're processing. So that's where this context converters come into play. This allows this is actually run as part of the operator itself, and this context converters will look at these scheduling contexts that arrive, and then they make sure that they're actually sent along with the message or the acknowledgement that flows through the data pipeline. And at every single operator, once you receive a context, either from upstream or from downstream, you would use that information to update your priority. Like you at every operator level, like at every stage in the things, the Cameo would actually have to maintain the priority information, like a two-level priority information, one at the operator level and one at the message level. So when such messages arrive with scheduling contexts, Cameo would the scheduling framework would actually pick up those priority information and update its data structures, so that it can run the scheduling algorithms on that. And again, like I said, the system also needs to provide an API. That way you can customize the priority generation process, like the way you look at the like determine the priority of a message could be dependent upon the scheduling the algorithm that you're trying to use. So we need a way to customize that. So the scheduling framework actually provides that API as well. So this is a diagram that I picked up from the slides, and this kind of captures what I just explained. So let's say if there is a if there are two stages in a pipeline, this is where we are starting. So and when the messages arrive to be processed, there's no context here, so we kind of build the context at source. We will add all the information, like let's say the local priority, the global priority information, and the fields that needs to be used by the priority generation algorithm downstream. So all of that information is encoded into the priority context, and it will be sent downstream to a downstream operator. And the downstream operator, once it gets build the context at the operator. So there's another. I mean, these are APIs that are provided by the Cameo scheduling framework, which the operators will be implementing and calling into. So this would now once the message has arrived here, you probably will have to calculate the priorities of the message depending upon the information that is available at that particular operator. So you kind of build a update the context based on the information that is here, and then process the request. When you say process, it will be the scheduler will use all of this information that is collected and makes his decision to pick up the highest priority process. And once a message that gets like processed, there's an acknowledgement that flows back. Along with the acknowledgement, you would also construct the reply context and shove in some like priority information that is needed upstream. So you kind of create the reply context and send it back to the upstream operator. And once if the reply if the acknowledgement contains a reply context, then it would use the contents of the reply context to update its bookkeeping here. That way, it like one of the things I think they mentioned about is that it will try to improve the cost of downstream, the C path variable that we saw in the equation. So to improve that, they use this information and learn some linear regressions on that, and then try to optimize that. So this is typically the flow. Like whenever a message is passing flowing down, you kind of provide the priority information and send it down, and the downstream operator would use that information and generate its own priority and schedule it accordingly. Once the message is scheduled, with the acknowledgement, we kind of send the information back up, so that the upstream prioritization scheme can improve its efficiency. So this kind of captures the overall flow. And I did not the bunch of results that are presented in the paper, I did not grok all of them. This is something that I could relate to quite easily, so I have just called it out here. So this is about like a multi-stage a data pipeline that is being executed. So there is the vanilla Orleans being used for that, and there's a FIFO scheduler that is being used, and then Cameo. So here you can see that. So the colored ones here are make up the stages for a given window boundary, and the gray ones are the next window messages from the next window boundary. So here you would see that the window boundary is kind of elongated, meaning that the next window, messages that fall into the next window kind of get processed before the previous ones in both these cases. And with Cameo, their observation was that there's a clear demarcation, like almost a good demarcation between the messages that fall within this. Like messages that fall within a prior window all get processed before the messages in the subsequent window, and like they claim that the query latency, but by actually having this topology awareness and query semantics awareness built into the system in determining the priority of the messages, they claim that the query latency is reduced by like almost 3 times for single query execution, and almost 5 times or 4.6 times for multi-tenant scenarios in multi-tenant scenarios. And there's also claim that they can weather the transient spikes by reducing the tail latency by so much. So yeah, I mean, that's pretty much I had. It's a summary of the paper, and maybe we can jump into discussions now.